Hi, I'm Michael Bartlett. I'm a senior undergraduate at the University of Oklahoma, and I'm planning on pursuing graduate school in the field of astrophysics. This summer, I worked with Dr. Zachary Slepian at the University of Florida on the topic of parity asymmetry in the cosmic microwave background. Now, just a quick overview of the project. When we say parity here, what we really mean is a reflection across all coordinate axes. So the big question we're looking into is whether or not our universe looks the same if you were to reflect it across the x, y, and z coordinate axes. In the past, researchers have looked into this in two main ways. They've looked at galaxy surveys, in which they've studied the 3D distribution of galaxies in our universe, and they've looked into the cosmic microwave background, which is shown on the right, which they've used to study the matter distribution in the early universe. The problem is that galaxy surveys have shown evidence for parity asymmetry in our universe. However, the cosmic microwave background has not. Our goal is to compare the 3D nature of galaxy surveys to the 2D nature of the cosmic microwave background to find a reason for this disagreement. Now, why would the dimensionality of the system matter? Well, let's consider a 2D shape like a triangle. If we were to perform a parity transformation on it, it would look like a reflection across the x and y axes. But if you look at this, you may notice that this is actually just equivalent to a 180-degree rotation. Now, let's consider an analogous case in 3 dimensions with a tetrahedron. If we perform a parity transformation on it, it looks like a reflection across the x, y, and z coordinate axes. But now, if we try and bring it back to its original position, we notice that we actually end up with a mirror copy of the original tetrahedron. The main takeaway of this is that in 2 dimensions, a parity transformation is the same as a rotation, but in 3 dimensions, they are unique operations. Using these properties, we have not yet come to a conclusive answer to the problem, but we have found several intermediate results. Notably, we've managed to simplify the problem down to a comparison of 2 sums, and we have further simplified the comparison of 2 sums into an integral over a sphere. From there, we have managed to solve several subintegrals that make up that main integral, though in the future we still have more work to do in regards to solving these integrals. I'd like to thank Dr. Slepian for working with me this summer and providing mentorship. Furthermore, I'd like to thank the National Science Foundation for providing funding for the program, as well as the University of Florida for housing the REU this summer.